This is one of my latest PCB designs and a very simple single rail to split rail DC power supply. Here you can see the results from the JLCPCB manufacturing and assembly, and in this video I'd like to show you how I went all the way from KiCad schematic capture and initial design idea all the way to layout and routing of this 2-layer board. I'll show you the actual uses of this device, how I ordered it with JLCPCB including assembly, and then we'll actually look at some real-world circuits to test this thing on. So let's get started. So here's the block diagram of the single rail to split rail DC converter. And effectively all that we're doing is taking some form of input voltage, for example from a 9-volt battery, which is somewhere between 6 volts and 12 volts, and we're feeding that into two separate regulators, buck and buck boost regulators, one after each other. The first one is this TPS5430, and that's a 5-volt step-down converter, and that gives us one 5-volt rail at quite a high amperage. Now we need 5 volts because the next regulator only has an input voltage range of about 6 volts. But it also of course gives us the 5-volt rail, and it's there to give us the 5 volts which then feeds this next regulator, which is a TPS65131. And this is a really cool regulator because it's a buck boost converter. So not only does it convert the 5 volts of the input to a plus 12 volt rail, but it also steps that down to a negative rail. In fact, it's a negative 12 volt rail. That means overall from this one PCB, for one input voltage between 6 and 12 volts, we get a 5 volt rail, we get a 12 volt rail, and we get a minus 12 volt rail. And all of them can supply quite a lot of current, so maybe I don't know, up to half an amp each I've spec'd it at. So this is really useful in particular for a lot of analog circuitry, specifically with regards to op amps, which typically require a positive and a negative rail. Now you can get away with doing a split rail biasing on op amps, but we can use this circuit, this PCB, to actually provide a plus and negative 12 volt rail. Thank you very much to JLCPCB for sponsoring this video. If you'd like to order some of these PCBs for yourself, including assembly, let me show you how. First thing you need to do is go to my GitHub repository, go to github.com/pms67, then click on repositories, click on banana split. Now you can either clone this repository or go over to this green button and click download zip and extract all the files. Once you've done that, go back to jlcpcb.com, either click order now or quote now. We'll upload the Gerber files, so click add your Gerber file, navigate to the Gerber directory in the Git repo, and I've already zipped it for you, bananasplit-gerber.zip, double click and it'll start to upload the files. Now once all the file upload has been completed, you can check the files using their Gerber viewer, which is quite useful, but I've already checked that for you so you can proceed with the order. JLCPCB has already filled in most of the information, including the layer count and dimensions, but now you can also choose the quantity of PCBs you would like to have made. Currently JLCPCB supports up to 30 PCBs to be assembled, but I'd just like to make 10 for now. So click on 10. PCB thickness we'll keep at 1.6mm. PCB color currently only green is supported for assembly. I'd strongly suggest with either going with lead-free hot air surface leveling or ENIG, so let's go with lead-free. All of this you can kind of leave as it is, except for remove order number, and we'll click on specify location. Last thing we need to do is click on SMT assembly, and we want everything assembled on the top side. I've put all the components on the top side, which makes the assembly much easier. We want to assemble 10 boards, and I've also already added the tooling holes, so click on added by customer. You can see these are the small tooling holes, 2 of them over here. So click confirm when you're ready. Next thing we need to do is actually upload the assembly information, so that's the bill of materials file and the footprint position files. Now I've already made them in KiCad, so click on add BOM. In the Git repo, navigate to the assembly folder, double click on BOM. Next thing, footprint position files, same thing, click on footprint position files. Once you're happy, click next. Now JLCPCB will show us our uploaded bill of materials data and what the automated system thinks it is. So typically you would go through the left and right side to make sure everything matches up, and I've already done that for you. So click on next, right at the bottom of the page. Now we can review the parts placement if everything's orientated correctly, and I've already checked that for you as well. So if you're happy with that, you can check out the price, and for 10 boards it's €64, which is incredibly cheap, €6.50 almost per board. All we have to do is ourselves is solder on these large screw terminals, but of course that's much easier than soldering one of these kind of QFN packages or something like that. So once you're happy, you can click Save to Cart. Okay, so now it's in our cart. Once you're happy, you might want to add some other orders of your own. You can click out Checkout Securely, and then proceed with shipping. And now we're going to look at the schematic to test the PCB and see how we can actually use that in action for an audio amplifier. So here's the actual test circuit we'll be looking at. And you can see it's very simple and just contains one op-amp IC. There are going to be some switching transients from the switching regulators and switching noise, and that's why we're performing some additional filtering via R1 and C1 and R2 and C2. And these both form low-pass filters. So a fairly small value resistor, but a very large value electrolytic capacitor. And we then use these filtered rails to feed our op-amps over here, so VCCF and VEEF. We also have some extra decoupling capacitors, 100 nanofarads each, which are close to the supply pins of the op-amp package. So we take the input from our voltage source, maybe an audio source and so on, and we feed it through this network here, which essentially C3 removes the DC bias, and we're just using R3 and R4 essentially to set the bias level at 0 volts, so it's pulling that to ground. Then we're feeding it into the first section of this op-amp, which is essentially just a unity gain voltage follower, so it acts as a buffer. Once we are done with that, we feed into the second stage, and that's a very simple non-inverting amplifier, so really nothing fancy. R5 over R6 plus 1 is the gain of this amplifier, so we can get up to about 100 over 10, and we get a gain of 11 at maximum, and we use C4 to limit the upper bandwidth. So C4 in parallel with R5, that actually forms a low-pass filter. So we get quite a bit of gain, and we get a bit of filtering action as well. Also C3 and the parallel combination of R3 and R4 together form a high-pass filter, so that sets the lower bandwidth of the circuit. R5 is actually a potentiometer, so a variable resistor. I've included R7 as a load resistor, and we'll take our output from there. Okay, so let's have a look at that on the bench. So here's our little test setup on the bench for our buck and boost converter board. So you can see here's kind of the original, and normally I'd screw on these 5mm pitch screw terminals, but for the sake of simplicity and time, for the first board as a test, just to see if everything's working, I've just soldered on quite a few stray wires. Doesn't look too nice, but it does the job. I'm feeding it via these crocodile clips from this power supply. Currently it's 7 volts, and it's drawing about 130 milliamps. And that's feeding into this schematic, or this circuit we looked at earlier. So a very simple audio amplifier using one op-amp IC with 2 separate op-amps. It's an LM358 with just a simple volume control, and then I'm probing that with an oscilloscope. So the oscilloscope leads are a bit longer than I typically like, but for this very simple low frequency circuit, that's absolutely fine. I'm also feeding this circuit from my phone as a function generator. So I do have a normal function generator, but just for the sake of simplicity, I'm using this. So I set it to 1 kHz sine wave, and that's going via this auxiliary cable into this kind of headphone jack, and I'm just using one of the 2 channels to feed into the input of the op-amp. So my peak-to-peak input is the yellow, and that's 860 millivolts, and the output is about 8 volts peak-to-peak. Now if I can toggle this potentiometer, and as I do, I reduce and increase the gain. So a very simple volume control, very simple amplifier. So as we can see from the waveform, it's actually pretty steady and fairly low noise, at least from this kind of perspective. So that's really nice. I mean, we've done a couple more stages in filtering on this breadboard here, but overall with just a tiny bit more filtering, some external resistors and capacitors, we can get this thing really noise-free, which is really nice. So you could even use this for fairly simple and basic audio circuits, as we've done here. So let's move over to KiCad, and I'll show you how I did the schematic, the layout, and the routing for this very simple 2-layer board. So here we are in KiCad, and as you can see, this is a fairly straightforward 1-page schematic, roughly sectioned into 4 sections. We have one regulator up here, one more interesting regulator over here, some sort of screw terminals, LEDs, and mounting holes. So let's go through it one by one. Let's start with this first regulator up here. So essentially I'm taking some sort of input voltage and I want to step that down to 5 volts. 5 volts because it's useful to have a 5-volt rail, and we need 5 volts to feed into this next rather special regulator, which we'll talk about in just a second. Before we go into this first regulator, I'm fusing the input, and that then goes into reverse polarity protection in forms of a P-channel MOSFET. Unfortunately, the gate source voltage kind of limits the maximum input voltage you can apply, and that's in this case 12 volts. So you could choose a different MOSFET which might have a larger VGS, or you could also use a Xeno diode to kind of clamp the VGS voltage. But I've just figured 12 volts is probably enough for me as a large input voltage. And then we feed from that reverse polarity protection into this switch mode regulator. So it's a step-down converter. The best thing to do with all of this is always just follow the datasheet. So this is the datasheet over here. It's a 3 amp regulator. It'll tell you everything about power dissipation, what kind of thermal ratings it has, and so on. It tells you kind of typical applications and application circuits. So what do you need to connect where? What size capacitors do you need to choose? What diodes need to be where? And what inductors? So my tip is just follow the datasheet. And this will tell you also how to size inductors. So it'll give you equations depending on what load currents you have, what input-output voltages you have. You can size the inductors, output, and input capacitors. One thing also switching regulators typically need is some sort of feedback voltage, which will then set the output voltage. And this is done via these resistors over here, R3 and R4. And from the datasheet, you can actually get the expression for the output voltage, which is R3 over R4 plus 1, times some sort of a reference voltage. And that turns out to be just under 5 volts, which for our needs is more than enough. So really simple, follow the datasheet, maybe add some fusing and add some reverse polarity protection. And the datasheet will tell you everything about what components you need to put where, and the sizes. Moving on from that, so we have 5 volts here. The 5 volts is then fed directly into this second regulator over here. Now all of this looks rather messy and kind of confusing, but again, the best thing to do is open the datasheet, and you can see again we'll have some sort of typical application schematics, and it'll tell you how to size the various components. It'll tell you why we have this MOSFET over here, why we need these inductors, and so on. It'll also again tell you how to set the feedback voltage resistors, for example R6 and R7, and R8 and R9, to get the rails, for example, plus 12 volts and minus 12 volts. And that's exactly what I did. I had to go fairly low with the input voltage to this regulator. This regulator only supports up to about 6 volts as its input. And it's really useful, this chip, because it generates this split supply for us. So we hardly have any work to do other than read the datasheet and figure out the component values. And that's pretty much all there is to this first and second regulator. The nice thing is they are also in stock a JLCPCB. Okay, so we have these 2 regulators. Other than that, of course, we need some sort of connections, and that's what these screw terminals are for here. So we have the input voltage, VCC and ground. We have outputs 5 volts, plus 12 volts, and minus 12 volts. And these are standard Phoenix 5mm pitch screw terminals. Other than that, I thought it'd be quite useful to just include some indicator LEDs. So for all the rails, we have a 5 volt rail, 12 volt, and minus 12 volt. I did red, green, and yellow. They each have their own respective forward voltage drop. For example, a red LED will have about 1.8 volts forward drop, and I wanted about 2 milliamps per LED. And that, for me, is typically bright enough. So I would just do 5 minus the forward voltage drop, 1.8, divided by 2 milliamps, and that'll give me about a 1K5 resistor. And repeat that same process for the green-yellow LEDs, and they'll have different forward voltage drops as well. Other than that, I always include the mounting holes in the schematic as well. And at the bottom here, I've kind of just done power calculations to make sure these regulators run within their limits. Okay, so the schematic, as you saw, follow the data sheets, add some terminals, add some LEDs, and that's pretty much it. So we can kind of have a look at the routing now. So let's move over to PCB New and check that out. So here we are in PCB New, and let's quickly go through the layout and routing I did for this board. As you can see here, this is the completed board. It's just 2 layers, so I only have front copper and rear copper, no inner layers. Once again, the datasheets will tell you all you need to know about layout, and this is particularly true for switching regulators. They will always try and show you how to connect the grounds, where you need vias, where you need to put the certain components, for example, inductors and diodes and so on. All I did was essentially follow this layout for this plus 12 and minus 12 volt regulator, copied it over to KiCad. Same thing you can find in the other regulator document as well. And that's pretty much all you have to do and kind of try and fit it into the space you want it to be. I wanted this board to be nice and compact and rather tiny, It turns out that this board is only about 32mm by 77mm, so that's pretty nice. It's a nice and small board. You can fit it into other small projects and other small enclosures to power any kind of analog electronics you might have that require split rails. So again, follow the datasheets, follow the manufacturer's recommendations is typically a good starting point. What I did in terms of routing and layout, first of all, of course, placed everything as the datasheet wanted it to, figured out the overall size of the board, placed my connectors at the edges far enough apart that they don't get in the way of each other when you're kind of trying to plug things in. What I also did on the rear copper layer, I put a large ground fill. So everything filled nicely with ground, and I also filled the top with ground as far as I could. So 2 ground fills, top and bottom. And that's typically what you would want to do in a 2-layer board. As you can see on that note, I also have a lot of these vias. So all of these vias you see here are pretty much just ground vias. And these are called stitching vias just to make sure you have a low impedance, low inductance path between all of the ground areas and ground fills. And that's generally a good thing to do. Spacing is fairly arbitrary. I don't want it too largely spaced and I don't want it too small spaced. Just something that looks kind of appealing. I've sectioned it. Essentially my input power terminal is over here. My 5-volt terminal is here, 12 volts and minus 12 volts. And that's kind of to fit in with the regulator positions. So this is the 5-volt regulator over here with a really large 47 microhenry inductor. And this is the 12-volt and minus 12-volt regulator over here. Well, a lot of my routing I did just with normal tracks, trying to make tracks as thick as possible where they need to be thick. I've also tried a new thing, which is kind of using copper pores to do routing. So I will add filled zones over here. And if you want to do a filled zone in a filled zone, as you saw my front copper layer has already got a filled zone on it, what you need to do, so if I double click on one of these zones, you need to change the zone priority level. So 1, 2, 3, 4, 5, which means zones can coexist within each other. And depending on the priority level, KiCad will then determine which one, of course, it prioritizes. Clearances, I've tried to make fairly large, so about 0.5 millimeter, thermal clearances and so on. They're approximately the standard values you will usually see in KiCad. I've kind of adjusted them a bit to make them a tiny bit larger. Also the thermal spoke width. So for example, if I switch the mode here, you can see the thermal spoke width is essentially for the plated through holes or SMD parts, how wide this track is here. So I've widened that up a bit because I'm carrying quite a lot of current through these traces. One thing, of course, you can do to see what kind of widths you need is use the KiCad PCB calculator. So if you open that up, you can go to track width. Say, I don't know, if I have a 1.5 millimeter track, I can see I can carry about 4 amps for a 20-degree temperature rise. So that's pretty good. We are only going to carry, at a peak, maybe 3 amps. So that's typically more than sufficient. But generally for power traces as wide as is usually physically possible. And you can see here, they're nice and wide, traces everywhere. I've used pretty much a lot of these copper pores to actually replace my traces. It makes it kind of easier to route, I find. Another thing I did, as you can see here, they have these edge smoothed corners, which is a really nice feature in KiCad. So if I double click on one of these copper pores, you can go to corner smoothing and use chamfer or fillet, don't know how you pronounce it, and then put in a certain fillet radius, and this will give you these nice smooth corners. Generally, that's a nicer thing to do, and I believe it's also more visually appealing. Yeah, so the routing, I'm pretty much following the datasheet recommendations. So as I showed before, follow this and you'll typically be safe. One thing with switching regulators is you want to kind of keep the loop area small. So keep things compact, make sure traces are as long as only they need to be. I try to also keep my routing constrained to the top layer as well. As you can see, most of this stuff here is red, which means it's on the top layer. I only very occasionally have these kind of short traces running on the rear layers where I really had to do that. I try to keep them as short as possible because you don't want to break up the main ground pore, which is the rear copper layer. You don't want to break that up too much. So I've done it in a small part here, a small part here, and unfortunately this rather long trace here. But it shouldn't and doesn't give too many problems. But in generally, try to route everything you can on the front layer, or on one of the layers, for a 2-layer board, and keep a solid ground plane on the other layer, typically the bottom layer. All the indicator LEDs are here, here, and here, so nice and visible. Screw terminals placed far enough apart. And that's pretty much all there is to the layout. One thing you can see here is also my bad attempt at kind of graphics. And this is actually silkscreen I did on on my iPad, and exported that as a graphic, and then imported that as a KiCad library, and I'll show you quickly how to do that. So you can do that by going to KiCad and then clicking this bitmap to component converter. Click on load bitmap. And for example, I have one of my, a really crappy logo here. I can just double click on that. And you want to determine the size you need on your PCB. So if I go back here, I can measure, okay, about here to down here is about 10 millimeters by 10 millimeters. So if I want a 10 millimeter by 10 millimeter silkscreen or graphic, I can adjust the DPI resolution down here. So let me try, I don't know, 250. Actually, that's not going to be 1024. That's still not large enough, or small enough, sorry. So about 2048 by 2048 will give me a size of 8 by 3 millimeters approximately. So you can vary the size by changing the resolution here. We want it exported as a kind of a library file, so PCB new, and we want it to be on the front silk screen. Now, if you want to preview what that looks like, because everything has to be kind of converted to black and white, that looks here, and you can change kind of the thickness of the lines by changing the black and white threshold. So you can see it kind of gets weaker as I move it further to the left. Once you're happy, you can click export, and export it as a KiCad mode footprint. Once you're happy with that, then you can add it as a library here, as manage footprint libraries, project-specific libraries. As you can see, I've already added a silkscreen library here. Once you've added that, you can click on Add Footprints, and just click anywhere. It'll start to load footprints. So once the footprints have been loaded, you can see here one of my libraries, and this is the one I used. So I can double-click on that, move it around somewhere, and place it, and that'll actually put the silkscreen on the PCB. And that's exactly what I did here as well. We can look at that in the 3D viewer, and you can see that's what the silkscreen then looks like. It's a crappy drawing of a banana and kind of the name of the board. And I'm sure you can do much better than I did, but yeah. So that's how you can add kind of custom graphics to your PCB as well. One more thing is, I mentioned before in the ordering stage that if you add this text here, so JLC 4 times, and then you can tell JLCPCB to put the order number there. I put it there because, as you can see in the 3D view, that is actually covered by an inductor. One thing as well you need to do for JLCPCB assembly is actually provide little tooling holes. Now they can do it for you, but I'd like to put them in spots where I know they will actually then be added. So I've just put 2, I think you need to put about 2 or 3 on the board. 2 is typically sufficient, and I put them in these corners there. You can either just click on Add Footprint and then place mounting holes, or you can go to the Edge Cuts layer and add a graphic circle, click somewhere where you'd want the mounting hole, the tooling hole, double click on it, and we need a radius of, I believe, 0.576 millimeters. And then just move it in a convenient place, and drop about 2 or 3 of them on the PCB. So that's pretty much all there is to this PCB design. So fairly straightforward, 2 buck regulators, a couple of screw terminals and LEDs, some silkscreen, a couple of vias, ground poles, and so on, and you're pretty much done. Again, basically just following the datasheet recommendations.